Hi everyone! In my previous video I talked about building an 8-bit computer entirely from scratch, and I thank you very much for all your comments. Today I would like to explain multiple things. First, I would like to give you a more detailed presentation of the hardware. Then I will give you updates about the next hardware for the project. Here is the latest prototype. This is the one I showed in the previous video, and I'm going to give you more details about it right now. So as you can see, it presents a micro USB port. This is for power input, of course. So it does not require any special adapter. Any phone charger will do the trick. There is a power switch just below it. Here we have an eFuse for protection. And here the small rectangle, let's focus a bit. The small rectangle is the oscillator, the 10 MHz oscillator. I also added a 40-pin extension port here, and we have a similar port here at the bottom of the board. So this one is only used for debugging, because it's more convenient to plug a wire here than try to plug a clip on one of the pins of the socket or of any chip. Here we can find the video port. So it's also a 40-pin port, and this one will currently only connect to the FPGA development board that I'm using for video output. Here we have a PS2 port for the keyboard. Well, it should be purple and not green, but functionally it's exactly the same. And here we have a user port with 8 GPIOs that can be used for any purpose. So now let's have a look at the chips. So here, and here we have 4 8-bit registers. So these chips are used for memory banking. Here we have the 512 kilobyte of static RAM. So it's a single chip. It's much more convenient than having multiple chips, and it's easier to manage, and it takes less space. Here we have the Z80 CPU. This is the 10 MHz version. Here we have the ROM, 256 kilobyte of ROM. Here we have the PIO, which manages the GPIOs. So as you can see, all the chips on this board are dual inline packages. So we have sockets, which makes it very easy to take them off and replace them or plug them back in. I haven't talked about the smaller chips. Well, these chips are logic chips. So for example, here we have 5 chips which are responsible for converting 5 volts to 3.3 volts. This is mainly used for this port, for the video port, because the FPGA only accepts 3.3 volt inputs or 3.3 volt signals. Here we have 2 logic chips. Here we have 4 logic chips. Here 2 shift registers, and here a NOT gate. All these chips are responsible for activating the right chip depending on the memory address the CPU is currently probing. So you may wonder, what is the empty spot here? Well, at first I wanted to integrate an FRAM. This FRAM. So an FRAM is a non-volatile memory that acts like a static RAM. It's fast, it does not need to be refreshed, and it has a long time data retention. So it was a perfect candidate for the board. However, the thing is, this chip that I'm showing you now is an old one, used one, and these chips are not made anymore. So this one is only 8 kilobytes, and most FRAMs today are either in smaller formats because they're using SPI bus or I2C bus for communication, or in other smaller formats than deep, so we cannot have some sockets to plug them in easily or we'll take them out. This is why I dropped the idea of using an FRAM. Instead, I will be using an EEPROM like this one. This chip is the 24FC256. Its main advantage over the FRAM is its price, its capacity, as this one is a 32 kilobyte, and its accessibility. In fact, it's easy to get 1 or 2 or even more. I will explain this choice in a moment. Now, let's take a look at the FPGA board. This is a development board, as you can see, and it embeds an Altera EP4CE10 FPGA. This is the most straightforward way to start with. I'm not using all its features. I'm only using the VGA output, of course, the 40-pin extension port for connecting to the main board, and also few pins of this port for the audio output. Additionally, in the future, I would like to use the micro SD port in order to read data from SD card or save data to the SD card. Now that I presented the stable hardware, the one I'm using daily, let me talk about the improvements I've been working on and the ones I would like to make. I will remove the FRAM spot and add a socket for the I2C EEPROM I showed earlier. A quick word on I2C, or inter-integrate circuit. I2C is a multi-master and multi-slave communication bus. In other words, it lets multiple master communicate with multiple devices, and thanks to only two wires, the SCL represented in blue and SDA for data represented in red. The other well-known communication bus is called SPI for Serial Peripheral Interface. It is also pretty simple to implement because we can communicate between one master and one multiple devices thanks to 4 wires. Back to the project. I made this choice of using an I2C EEPROM and not an SPI for multiple reasons. SPI can go up to 10 MHz, whereas I2C is using 100 kHz for standard mode and 400 kHz for fast mode. There are also fast mode plus and high speed mode, but this is less common and none of them reaches the SPI's 10 MHz, so I will not talk about them right now. But the fact is I will use a GPIO to simulate the SPI or the I2C. So how does it work? I will be using a GPIO from the PIO, which is the chip that manages the IOs. How does it work? So the first thing I wanted to do is try to simulate one of this bus and try to benchmark what's the fastest frequency I could reach with the Z80 CPU. So what I wanted to do is generate a clock signal. It's pretty easy. First, I output a high on one of the IO, then output a low, then high again, then low, well, you understand. And at the end, I just check the speed and the frequency. And here I got 300 kHz. This is the maximum reachable frequency for me. In practice, the speed will even be lower because we need to process data before sending them on the wires. SPI would never reach 10 MHz on our board with a software implementation. Second reason, SPI requires 4 wires, as I said earlier. It will require the clock, the MOSI, master out slave in, MISO, master in slave out, and CS for chip select. Whereas the I2C will only use 2 wires. But what does it mean? Okay, let's check. Let's say this master is our board and this device is the I2C EEPROM. We can connect them thanks to 2 wires on I2C. And what if I would like to add another device? Here. Well, it's pretty easy. I just need to connect the SDA to SDA and SCL wire to SCL wire. And that's it. No more addition. However, for SPI, I have my board here with 4 wires, my EEPROM, SPI EEPROM, and the 4 wires I talked about earlier. But what if I want to add a device? I can still add a new device and connect the clock to its clock, the MOSI to its MOSI, and MISO to its MISO. But what about the chip select? We cannot use the same chip select as this device, else both devices will be activated at the same time. Well, we have to use another GPIO from the master. So it means that one device needs 1 GPIO. So if I would like to connect 3 devices to the main board, I would need 3 GPIOs. And so this is why I chose to integrate an I2C bus on the main board. It will save me more GPIOs, and the fact is I don't have a lot of GPIOs with the Z80 PIO. So this is the representation of the PIO. We have 8 GPIOs on port B and 8 GPIOs on port A. I will be using port B for system IOs. Thanks to the pins saved using I2C and not SPI, I'm also implementing a UART protocol. Then it will be possible to communicate between Zeal board and another computer, microcontroller, or even another Zeal computer. Okay, regarding the main board improvements and the chips, I will get rid of the level shifters because they are only used for the FPGA, so instead they will be part of the video board. The CPU, the ROM, the RAM will not change because they are the heart of the project. But for logic chips, I plan on replacing them with some custom logic chips. You see, the role of logic chips is to decide who between the ROM, RAM, banks or video is going to listen and to respond to the CPU when a request comes out. The thing is, each logic chip has one functionality. It's either a NOT gate, like here, or an OR gate, like here, or, well, you see. What I'm going to use for this is a PLD or programmable logic device. I'm going to use this one. The fact is, this chip contains as many logic gates as all these chips. So you have a rough idea on how much space this will save. And cherry on the cake, this chip can be programmed with this, which is the one I'm using currently to flash my ROM. Something else that I will change on this board is the oscillator. I would like to use this one. It's bigger than the one I'm using currently, but it will be easier to replace it or to install it simply because it has longer pins. No more waiting. Here is the next prototype I designed. The PCB size has been reduced by 68%. There are less chips, but more functionalities. The chips are still easily accessible and replaceable thanks to the sockets. As you can see, I'm using the 10 MHz oscillator I showed earlier, so this one is bigger and it's much easier to solder than the SMD one. In the middle, we can see that there are two PLDs that will manage the whole logic of the board. The big fuse is gone. The new one is smaller but can still be replaced without soldering. On the top, we can see the 4 ports we've talked about until now. So there are the 40-pin extension port. Then nearby it we have the system port, which has the UART pins RX and TX, and also I2C, SCL and SDA. And just nearby it we have the user port, which has the 8 GPIOs that can be used by the user. And finally, we can find the PS2 port. Well, I don't have any 3D model for it, but you can see the footprint on the PCB. You also may have noticed that on the right side of the board there is another connector. This is the video card connector. Indeed, during the past month I have also been working on a custom FPGA board. You know what? Let me show you the design. Alright, so this is the design of the custom FPGA board I've made. And well, it's not very clear now. Let's have a closer look. Yeah, that's better. Okay, so we can see we have the same FPGA as the development board. We have a 16-bit VGA port. Here we have the level shifters here, so which have been moved from the main board. We have some LEDs, micro SD slot here, the potentiometer for the sound, and the 3.5mm jack. So this is the video card I will be using for the next prototype once I will receive it and test it. So that's it for this episode. In the next episode, I will talk about the improvement made to the software, the future additions, and I will still give you some detailed explanation and demos. Some of you asked for different type of videos, from how-to videos on how to make such an 8-bit computer to tutorials on how to make 8-bit programs and games. I'm still considering any kind of idea, so let me know in the comment what you would like to see on this channel, or you can give me any other feedback. Thank you very much for watching, and see you soon.